Hello and welcome to the ECE141 Lab 11 checkoff for the Binary Search Tree Lab. Here we'll be going through both a code demonstration to see how the code individually works, an analysis of the insertion node, and a general understanding of how the binary search tree works for the contents of both the report and the checkoff. So in terms of what the code is actually doing, we have two key pieces of information. One, a node, which each node has data, a pointer to the left and right of its given self, and an initialization constructor which sets data equal to some input data from the user, null for left and null for right. In a binary search tree class, we create a pointer node to root. Basically, we want to track if our root, right, the pointer node we've made to the root, we're going to create an empty tree at first. We can then receive this by getting the root. So we know that if there's any value that's actually in the binary search tree and it's just a singular value, we can always receive the root outright. We take this in a step further by inserting the node, and then we run two individual functions per insertion, per finding, and find the largest node. This is why this is important. In the context of each individual type of function, we want to find specific pieces of data. What does that mean? It means that when we run a particular insertion node, we want to make it easier for both us and the user to track what's actually being inserted into the binary search tree. Here, we don't necessarily have to put in a root every time as long as we have a pointer to the root data and we can ensure it's being inserted correctly. So which is why we have the sub insertion function, which is taking the data the user wants to insert into the binary search tree, calling the insertion node function, and running this over again. Here, for the insertion node function itself, this is going to be running at log n time complexity. The reason why is because n log n is going to run for a recursive function, but critically in that case, if we're inserting the node, we want to ensure it's being inserted correctly. So log n accounts for the fact that when we run things recursively, it's going to be splitting the contents of the binary search tree into an array or to a list. It's going to look at each pairing of data, and then it's going to run for the entirety of that data, which is where the n comes from. It's running for n times each individual element, log n for splits. Here though, because we're individually checking is the data reflected at the, so if the data is less than the root or if the data is greater than the root's data, that's where we place it. In other words, we're checking to see whether the left or right piece of information is going to be reflected in terms of the data the user wants to input. So critically, that shrinks the time complexity of this down to simply log n, because it's not doing that extra step of needing to check for the entirety of the array. We already know it's going to be running at log n because the n log n would have to run it in either in an unsorted fashion or it's not taking the arrangement of data into an account. So we can continue on from there. We continue on from here by showing a few more pieces of information. For one, we have the print tree, right? The print tree is returning the pieces of data by showing either the left or right of the given element and then outputting that data. Find node then goes through and essentially does the same thing as insertion, but in this case it's just returning whether or not there exists a piece of data that is there. In other words, it's returning either a specific node for either the left or right data, depending on whether or not the data is larger than the root, or the root itself if there exists data in that given qualifier. So for example, if there's nothing in the root, then we know that there can't possibly be anything in the rest of the binary search tree, so we don't even check it. This bool find function does the same thing as the insertion. That makes it easier for us to actually simply input a value or input a piece of data that the user then goes in and looks for. The largest effectively does the same thing by checking if the current element is the root. So it's basically checking if the root is null and then goes in and continuously checks if there's a larger value than the furthest rightward element, which based off the way we inserted it, the rightward element should be the biggest, but sort of for the contents of the binary search tree. So it would be in the proper order, but the hope would be that based off the way we've inserted it, that the largest value should be in relation to the rest of the binary search tree, the right value. And then we return that root in this find largest function here. In the main, we create a binary search tree, tree length, tree data, the tree value that they might want to look for. We input the amount of elements they want for the length that they want the tree to be. We input that into a post order, and then we have the largest element found by calling this function, and then they find we check if this value exists by using that find node function up here. So let's do a demonstration. So if we have 10 elements, and we do this in reverse order, what we see is that in our post order, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can see that here. If we have this particular binary search tree, where 10 is the node, the root node, and everything else is successively paired into left and right children based off that, we see that 1 is the leftmost child. So it starts with this left. Then we say what's the subsequent right, right? So in this case, the next right child would be 2. Then we're looking at that particular node that would exist after that point. And then we sort it in by those pieces of information. The largest element would then still be 10. If we want to find a number to look up, say we look up 5, 5 would be found within the context of this array. But say we wanted to do an element that did not exist, we know that in this case, right, we see the same idea. 1, 3, 4, 21, 5. It's doing in a post order based off of the orientation that we've set this up with. So 5 being the root, 4, 3 being its children, and then 21 and 1 being the children of 3. So then it's going to go 1, and then go to the next value, and then go to the next value from there, and so on and so forth for that entirety of the tree itself. But if we look up a number like 50, 50 is not a member of the list, hence is not present. And that is the checkoff. Thank you.